Welcome. Right now we're going to look at implicit differentiation. So I want to take the opportunity to try a simple example here with you, so hopefully you understand. Now consider the implicitly defined curve x squared plus y squared equals 1. So this is the unit circle with center 0, 0 and radius 1. So this distance is 1. Okay, and so what I want to do here is calculate the slope of the derivative, the slope of this curve at x equal to 1 on root 2. Now, notice first that this is an implicitly defined curve because we do not have a function here. It fails the vertical line test, meaning that if I take a vertical line that intersects this, there are two intersections rather than only one. And so it's not a function. Okay, so that tells us that we need to apply methods for implicit differentiation. And so one way to do that is apply d on dx throughout the equation and use the chain rule. So another way to do this would be to solve this function for y, but you get two answers. You get plus or minus the square root of 1 minus x squared. So in other words, you take this and you write y squared is 1 minus x squared. Then you take square roots. So you get plus or minus the square root of 1 minus x squared. Now, using ordinary methods of differentiating a function of one variable, you can solve this problem. But you've got to split this up into two functions, one where the function represents the top half and the other where the function represents the bottom half, right? So you can form two functions out of this circle. Okay, so that would be y1 is plus the square root of 1 minus x squared, and y2 is minus the square root of 1 minus x squared. So let's differentiate these, because we can write this as 1 minus x squared to the power of a half, and this one as minus 1 minus x squared to the power of a half. Now differentiation involves us pulling down the half, subtracting 1 from the exponent, and multiplying by the derivative of that inside function. So our first derivative is 1 half 1 minus x squared to the power of 1 half minus 1, which is minus a half, and then multiplied by minus 2x, which is the derivative of 1 minus x squared. And so we simplify this, canceling the 2's, and expressing this with a denominator of the square root of 1 minus x squared, we've got minus x over the square root of 1 minus x squared. And similarly with the bottom half, well, this time we have minus 1 half 1 minus x squared to the power of minus a half multiplied by minus 2x. And this one we can express as minus x over minus the square root of 1 minus x squared. Okay, I've got two minuses here. This gives us a plus because there are two minuses, but I've kept the two minuses in there for this one because y2 is minus the square root of 1 minus x squared. So we can write this as minus x over y1, and we can write this one as minus x over y2, right? Which allows us then to easily take the value of the point, sub into the x and the y value, and get the slope of this curve at the point 1 on root 2, 1 on root 2. For example, among all of the other points on the circle except for these ends. Okay, so subbing those two values into this formula, we have minus 1 on root 2 over 1 on root 2, which is minus 1. Okay, so our slope of this is minus 1. That is, the slope of this tangent at the point 1 on root 2, 1 on root 2 is minus 1. Now for this one, where we're looking is, so remember how this is ambiguous here. So we're not actually talking about this point up here anymore. We're talking about a point way down here when we're referring to y2. And so the corresponding y value is minus 1 on root 2. And the fact that we've got a minus in here gives us a plus. So in other words, minus 1 on root 2 over minus 1 on root 2, and we have 1 for that slope. Okay, so this is a slope of 1 at this tangent line. All right, so now let's use possibly a more sophisticated method, because we've got a nice simple formula for doing this. So dy on dx is minus f subscript x over f subscript y. Okay, so we define f of x and y by taking this equation and taking that 1 over to the left-hand side so that we have 0 on the right-hand side. And so that's how we get uppercase F. Now we differentiate that partially with respect to x, and you can clearly see that you have 2x, and then with respect to y, partially, you have 2y. Okay, so then subbing into this formula, we've got minus 2x over 2y, which is minus x over y. And that's the same as we got via this method. All right, so that was really easy, and then you can just sub in any point you like on this except for these endpoints, because they are points where y, whoops, that's the x-axis, but that's where y equals 0. And then this is our y-axis here. Okay, great. Now let's talk about the other method we referred to earlier. So we can apply, so let's say alternatively again, apply d on dx to the equation. Okay, and what happens is we get, for this derivative, we have 2x, and then for that derivative, we need to use the chain rule, so that's dy squared on dy, dy on dx. The derivative of 1 is 0. Okay, now this here is 2y, we've got 2x, so we end up with 2x plus 2y, dy on dx is 0. And then we can solve this for dy on dx, right? So almost as easy as this, I would say. All right, now this requires the chain rule for multivariate functions with partial derivatives, right? So, and you apply this when f and y are functions of some other letter, say t. All right, now I'm going to show you a more sophisticated example, which is one like some of the ones you're doing. It just requires the multivariate chain rule. All right, so if f of x, y, and z equals 0 is a function of 3 variables, and f gives z implicitly defined by z equals some other function of x and y, then using the chain rule for partial derivatives, where the input values are functions of some other letter, this is what we have. Right, now the right-hand side here is 0, so taking df on dx gives 0, and then our chain rule here has all of these matching, you see that? And it's taken with respect to x, so that's why we have an x here. This is an x, 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 And over here we've got an x. All right. And now dx on dx is 1, and this should be shifted over, so let's write that over here. Cross this out. dy on dx, that's 0. And so what we have then is f subscript x, this here being f subscript x, this being f subscript y, and this being f subscript z. So f subscript x plus f subscript z times dz on dx is 0, and that gives us this formula here. Similarly, we have this one. Okay, so let's have a look at an example. Consider the surface x squared plus y cubed equals z squared. Calculate dz on dx at the point 1, 1, root 2. Okay, where is that? Well, there's a little black point here, but let's make it more visible. All right, there we go. And I even have this somewhere up here. Yes, there we are. And so I can show you around. There's our little point. Okay. Now, incidentally, you'd have to be careful here because it looks like our partial derivatives may not exist, right? Like on the circle where we had the two sides of the circle up here have y equals 0 there and y equals 0. Similarly, we could have similar problems in here. All right, so it does require some care. The partial derivatives may be 0. All right, so calculating dz on dx, we're going to use this formula. Now notice the x and the x match across the diagonal, and the z match across the diagonal. Similarly here, y and y, z and z. Okay, so that's a way to remember it, and we have a minus sign in it. So we're going to use dz on dx is minus f subscript x over f subscript z. Now we need to calculate these derivatives, so let's do that down here. F subscript x is just differentiating this partially. Well, we actually need to set out an f, don't we? So f of x, y, and z is equal to x squared plus y cubed minus z cubed. All right, so f subscript x then is 2x. F subscript y is 3y squared, and f subscript z is, hang on, that's a square, isn't it? So minus 2z. Okay, so we can take these into this formula, and we get minus 2x over minus 2z, and so that's x over z. Right now, at this point, so let's use this notation, meaning that we're subbing in the values of this point. Okay, so we sub in x is 1 and z is root 2, so we have 1 on root 2. Okay, and that's our slope, where we're treating y as a constant.